All right, so let's try our best to talk our way through example 3 here, where we are going to end up with complex roots. So we're going to end up with answers to this equation, this quadratic equation, set equal to 0, that are not real numbers. This is going to harken back to our lesson that you had from me on complex numbers. So if we look at that equation, 5x squared plus 8x plus 11 equals 0, let's think about a couple of things. First of all, picture in your head, is this upward or downwards facing? Okay, based off that a term, which is positive 5, we should imagine we have an upward facing parabola. Now let's think about what is our y-intercept. If we have x equaling 0, which is where our y-axis is, right? Our y-intercept always occurs when x is 0. Well, in this equation, like in all quadratic equations, when we set x equal to 0, our a term and our b term disappear. So 5x squared and 8x both turn to 0 if we plug in 0 for x, and all we're left with is 11. So I end up with a graph that looks like this, where we are positive, we're crossing over at 11, but this graph should never touch the x-axis. This graph is not going to have any real roots. That is to say, when we say this equation equals 0, on the real number axis, the real numbers which define our x-axis and our function's axis, which you might call y if you'd like, these are all real numbers. This is a real number coordinate plane. So if we have a quadratic equation like this, and as in the problem, we set it equal to 0, we are not going to find a real number solution. Let's walk through those steps there. So first of all, simply enough, we just plug in our values like we've been doing. So if we walk our way down to that third line where things simplify to -8 plus or minus the square root of -156 all over 10, we end up with a situation with a negative square root. Now, since we've already looked at complex numbers, we know what to do with a negative square root. We can break that into its factors, one of which is the square root of -1, which we define as that letter I, the imaginary number. Okay, in that fourth line, we end up with the square root of -1 times the square root of 4 times the square root of 39. Square root of 4 is our perfect square, so we can simplify that to 2. Square root of -1 is our I, so that's why in our fifth line we see 2i. Square root of 39, well, 39 is a prime number, so that doesn't go anywhere. And we can simplify in those last two lines by dividing everything on the top and the bottom by 2, just to simplify the numerator and denominator. We end up with a complex number as our solution. We have -4 plus I square roots of 39 and -4 minus I square roots of 39, all divided by 5. So those would not be things that I could plot on my real number plane, but if I wanted to create a graph that dealt with complex numbers, I might be able to put it on there. We are not going to do that at this time.